Hello everyone, myself Naman Khetan, and today I am gonna talk about TorsioSquid, which is a project based on modeling squid propulsion system for a soft underwater bot. So the mantle is a part of the squid mainly responsible for its propulsion. It works in two strokes. In the intake stroke, the mantle swells up, filling itself with water, while in its exhaust stroke it expels out the water to create a thrust force for its forward movement. I choose mimicking of squids because they are compact creatures that move rapidly while using energy efficiently. These are the properties which will be suitable for an underwater bot for the application of exploration and surveillance. So this is the basic structure of my underwater bot and the forces involved in it. So the shell has been of a semi-ellipsoidal shape, which will be made up of Ecoflex material. It has been divided into two parts. The upper one is called the apex, in which all the electronic items of the bot will be situated completely isolated from the water which will be intake. And the bottommost part is the one having the shaft of the linear actuator. uh, these are the Bowden cables which are situated between the shaft of the linear actuator and the apex. When the shaft has been in its backstroke, it will exert a force F actuator on the Bowden cables. Now these Bowden cables are at a helical angle with the apex. Due to this F actuator will be divided into its two components, the cos alpha and the sin alpha components. Now the F actuator cos alpha will create a torsional movement on the shell, while the F actuator sin alpha will cause a translational motion of the shell in the downward direction. As both of these movements will be happening simultaneously, they will be responsible for volumetric deformation of the shell, thus expelling out water, mimicking the exhaust stroke of the mantle. Now, when the linear actuator will be in its forward stroke, uh, the shell will restore itself to its full volume and intake of water will happen at that time, thus mimicking the intake stroke of the mantle. Thus, in this way, the whole mantle movement has been replicated in TorsioSquid. So moving forward, these are the basic performance parameters and the boundary conditions I have used for my simulation. Uh, so the first one is the thrust force, the force generated due to the exit velocity and the mass ejection rate. And for to calculate mass ejection rate, we need volumetric deformation. Now to find out the volumetric deformation, I have used the eigenvalue buckling analysis. The translational and rotational loads are the boundary conditions I have applied in the analysis. So let's jump onto the analysis part. So talking about the analysis, I have used the ANSYS static structural, which is mainly based on finite element analysis. So first of all, I imported the geometry of my semi-ellipsoidal shell in the ANSYS static structural and assign it the material properties of Ecoflex material using the U first order material model. After this, the meshing has been done using non-linear mechanical, and the element size has been chosen for optimum balance between the model accuracy and the computational load it has to be managed. The whole simulation has been divided into three stages. The first stage is the analysis A1, in which a pre-stress of 1 degree rotation has been applied. So as you can see here, the boundary conditions. So here the fixed support has been applied at the base, uh, while the pre-stress force of 1.25 Newton has been applied here, and this remote displacement of 1 degree rotation has been applied. So After this, on solving the whole analysis, we will get these uh, parameters, on which the most important one is the total deformation. So moving forward onto the second stage of the analysis is the eigenvalue buckling analysis. This analysis has been done to create geometrical imperfections in the shell. For this, I imported the pre-stress model into it and use the non-linear static structural here. So as you can see on solving it, this is the total deformation we are getting, and you can clearly see the difference in the total deformation of eigenvalue buckling analysis and the pre-stress analysis. So this shows the geometrical imperfections created due to the pre-stress condition which we have applied. Now moving on to the analysis A3. So in this one, the geometrical imperfected model has been imported here, and the loads applied here are the translational and rotational loads mentioned earlier. These loads have been applied in time steps of 10 seconds uh, to generate the folds in the semi-ellipsoidal shape, replicating the volumetric deformed state of the underwater bot, uh, which of the underwater bot, which it will be when the linear actuator will be in its backstroke motion. So here also the fixed support on the base has been applied. The force of 1.25 Newton is like uh, replicating the force due to the gravity on the shell. And the remote displacement, in the remote displacement we have applied the translational and rotational loads. As you can see here, these are in the time steps of 10 seconds. On solving this, we will get the total deformation. So here you can see the animation. So both the rotational and translational load have been simultaneously acting on the shell, creating the total deformation on the shell, and these are the and uh, these are the geometrical imperfected folds created in the semi-ellipsoidal shell. So due to these folds, there will be a major volumetric deformation which will expel out the water. Now to calculate the volumetric deformation, what I did is that import this deformed state of analysis A3 of the shell in SolidWorks and compare it with the initial one. Uh, the initial one, uh, this one, and calculate the volumetric deformation delta V. In this way, I get the volumetric deformation and calculate all the other performance parameters. Uh, the one additional thing, which we can add here is the usage of the nozzle to increase the exit velocity. As I have shown earlier, that the thrust force is dependent on the exit velocity. Thus, increasing the exit velocity will be advantageous for us. Now, to increase the exit velocity, we can add a semi-ellipsoidal shaped nozzle of exit diameter 50 mm. We did a fluid analysis for this, and we did a fluid analysis for this to verify our results on exit velocity, and we get good results on this 50 mm exit diameter. Thus this is an improvement we can do, and these are the results and conclusions after adding the semi-ellipsoidal shaped nozzle of 50 mm exit diameter to increase the exit velocity. And based on this and the delta V from the simulation, all other things have been calculated. As the whole thing have been based on simulation and modeling, to verify these results we use a mesh convergence error. in the ANSYS simulation tool by decreasing the element size of the uh, mesh, and to do the whole simulation again. Through this, we only get a 0.7% mesh convergence error, which gives us a quite a good reasonable accuracy for our model and the results we have found. So, thank you everyone. That's all, and I hope you like all the detailing of this project.